This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is motor nameplates. Our objective is to learn to read and interpret pertinent manufacturer, electrical, and mechanical information displayed on a motor nameplate. This lecture operates under the assumption that viewers watch the Motor Family Tree lecture, available at the Big Bad Tech channel, as a passing familiarity with three-phase AC electrical power and rotating mechanical power calculation and measurement. If you haven't watched these lectures yet, or only dimly recall their contents, please take the time to do so now. As you are no doubt aware, the motor family tree is a gnarled and expansive beast with numerous branches containing many different varieties of motors, each with their own peculiar natures and performance characteristics. This lecture primarily deals with three-phase AC squirrel cage induction motor nameplates for the simple reason that three-phase AC squirrel cage induction motors are the most popular rotating electrical actuator of choice for industrial applications. Additionally, a majority, but not all, of the entries in a three-phase AC squirrel cage induction motor nameplate are common to a number of other motors. As we introduce different types of motors in later lectures, I'll make sure to highlight important performance differences we encounter. For now, consider this lecture a general primer on the subject. A motor nameplate is a mini data sheet affixed to a motor in question describing its most important characteristics at the rated condition. In the event a motor is damaged, one can order an exact replacement or, lacking an exact match, interpret the motor nameplate entries to find a comparable replacement from a different manufacturer. In a perfect world, all manufacturers would utilize a common template, thereby enabling readability and interchangeability, but they don't, and it is the wild, wild west, and absolutely anything and everything goes. This being said, most manufacturers have enough sense to include the most important information, even though it might or might not appear in the same location. There's a bunch of different information on motor nameplates, but I like to classify each piece of data as belonging in one of three different informal categories: manufacturer information, electrical characteristics, and mechanical characteristics. Some motor nameplates also feature additional optional information. This lecture will restrict itself to discussing the most common and important entries. Before we do, let me make one point absolutely clear. A motor nameplate is not a data sheet. It is a mini data sheet for one single point inside a motor's larger operational range. This point is known as the rated condition. At the rated condition, the motor produces its rated mechanical power, rated torque, and rotates at its rated speed. The motor nameplate is a snapshot of those properties one might expect to observe at or around the rated condition. At the rated condition, a motor might be expected to draw the rated current at a specified power factor and operate with a specified efficiency. Operated at anything other than the rated condition, in excess or below the specified point, a majority of the entries on a motor nameplate are subject to change. For example, if an induction motor is excessively overloaded, we might expect its speed to decrease, current to increase, and efficiency to decrease, among other effects. Data at other than the rated condition is customarily not found in the motor nameplate, but rather it can be found in the motor's associated data sheet. A motor's complete data sheet will specify properties for a range of operating conditions, customarily on one or more charts. We'll examine motor data sheets and properties at other than the rated condition in later lectures. Again, the rated condition is a single point inside a larger operational range. The entries in a motor nameplate assume this rated condition. What's nice about this fact is customarily motors are operated at or around the rated condition because that is what the motor has been specifically designed to do. Why would you regularly overload a cheaper 3/4 horsepower motor with a larger 1 horsepower task? The 3/4 horsepower motor won't be as efficient and most likely won't survive repeated use. Why would you ever underload a larger 5 horsepower motor with a smaller 1 horsepower task? The oversized motor is more expensive, heavier, and most likely won't be as efficient. If you've got a 1 horsepower task, buy a 1 horsepower motor. At or near the rated condition, everything in the motor nameplate should be reasonably accurate, and if it isn't, something is wrong. In this sense, motor nameplates make handy troubleshooting cheat sheets. Let's take a look at the manufacturer information category first. Manufacturer, model, and serial number. This basic information is comparable to the make, model, and VIN number of a car. The manufacturer is the company that made the motor. The model number, or sometimes catalog number, is specific to that manufacturer. It means only something to them and not any other manufacturer of similar motors. The model number is that manufacturer's means of coding that specific style of motor, and it is also useful for finding replacement parts for that specific style of motor from that specific manufacturer. The serial number, if it appears, is a unique identifier for that particular motor. Ideally, a manufacturer would be able to look up that serial number using their historical database and tell you when and where it was manufactured, whether it is or isn't under warranty, or whether that production run this particular motor was part of has any known faults or issues. Like, let's say, an annoying tendency to burst into uncontrollable flames. Here's an example motor nameplate. Looks like this model W0881709 motor was made by Hampton, and this particular motor's serial number is 530-75185. The next category on a motor nameplate pertains to the electrical aspects of the motor in question. The most important of these entries specify phase, frequency, voltage, current, power factor, efficiency, Inrush code, and connection diagrams. Phase. The phase entry specifies if the motor in question is intended for use in an industrial three-phase AC environment or a residential single-phase AC system. Compare and contrast these two 1-horsepower motor nameplates. Even though these are both 1-horsepower motors that run at the same speed, they are not equally applicable because this 1-horsepower motor necessitates three-phase AC, whereas this 1-horsepower motor necessitates single-phase AC. Frequency. The frequency entry specifies the excitation frequency the motor in question is intended to operate with, ordinarily 60 Hz in the US and 50 Hz in the EU. All entries in the motor nameplate are specified at this particular excitation frequency. As we learned in the rotating magnetic field lecture, available at the Big Bad Tech channel, synchronous speed, the speed of the stated rotating magnetic field, is directly dependent upon excitation frequency. Motors operated at a higher frequency rotate faster, whereas motors operated at a lower frequency rotate slower. Related to this fact, some motors can be used in both 50 Hz and 60 Hz systems. If so, a manufacturer often splits the entries on a motor nameplate to specify properties at 50 Hz and again at 60 Hz. Here's an example of one such motor. This nameplate has a column specifying properties at 60 Hz and again at 50 Hz. As one might expect, the rotational speed at 60 Hz is faster than when operated at 50 Hz. Voltage. This entry specifies at what voltage a motor is intended to operate, allowing for a 10% tolerance. For three-phase AC motors, this is the larger line-to-line voltage, and it is not the smaller line-to-neutral voltage. For example, consider a motor intended to operate with a light industrial three-phase AC system characterized by 120-volt line-to-neutral and 208-volt line-to-line. This motor would be specified as suitable for 208 volts, regardless if that motor is configured in a Y or delta. Again, the voltage specified on a motor nameplate is always the three-phase AC larger line-to-line voltage. The 10% tolerance stems from a NEMA requirement that a motor deliver its rated horsepower at plus or minus 10% of the nameplate voltage. For example, consider a motor with a nameplate voltage of 200 volts. Allowing for the 10% tolerance, this motor should be able to deliver the desired mechanical output for systems down to 180 volts or up to 220 volts. This motor would therefore be suitable for a light industrial three-phase AC system characterized by 120-volt line-to-neutral and 208 volts line-to-line. The slightly lower nameplate voltage value of 200 volts ensures the motor has enough punch when it's hooked up to the higher nominal system voltage of 208 volts. Oftentimes, a motor nameplate includes two entries in the voltage field. If so, this means this motor is a dual voltage motor, and pending proper use of the connection diagram, which we'll examine later, the motor can be wired for either low voltage configuration or high voltage configuration. Dual voltage motors allow for a degree of flexibility for different electrical distribution systems. Here's an example of a 2-horsepower motor with a dual voltage rating. When windings are wired in parallel for a low voltage configuration, this motor can run at 208 volts up to 230 volts with a 10% tolerance. If, however, the windings are wired in series for a high voltage configuration, this motor can run at 460 volts with a 10% tolerance. Current. The current entry on a motor nameplate specifies the amount of current drawn per phase when the motor is operated at the rated condition. As with the voltage entry, dual voltage motors often have two entries in the current field, one for the low voltage configuration and another for the high voltage configuration. In our previous example, this 2 horsepower motor draws 6.5 amps per phase, while in the 208 volt low voltage configuration, 6.2 amps in the 230 volt low voltage configuration, and only 3.1 amps per phase, while in the high voltage 460 volt configuration. We'll discuss electrical power in a moment. However, it should be noted that the lower voltage configurations draw more current, whereas the higher voltage configuration draws less. Given power is voltage times current, this should make sense. Lower voltage with higher current yields the same power, as does higher voltage with lower current. Again, I must remind you the current entry in a motor nameplate specifies the amount of current drawn by the motor when the motor is operated at the rated condition, or to use a similar term, fully loaded. For this reason, rated current is sometimes referred to as full load amperes, or FLA. If the motor is underloaded, we might expect line current to decrease, whereas if the motor is overloaded, we might expect line current to increase. Anything in excess of the rated current would therefore be considered an overload condition. Momentary overloads aren't ordinarily an issue. However, sustained overloads produce excessive heat and may damage the motor insulation over time. It is for this reason motor starters incorporate not only a contactor, the means of making and breaking connection, but also a means of protecting the motor from sustained overload conditions, called an overload relay. We'll discuss motor starters, contactors, and overloads in later lectures. Some motor nameplates include accessory information about current. If a nameplate includes the accessory entry NLA, this is the no load amps, drawn while the motor is free spinning and experiences no oppositional torque. If a nameplate includes the accessory entry LRA, which stands for locked rotary amperes, this is the inrush current drawn when the motor is first started in a standstill or locked rotor condition. Inrush current is many times that of rated current. Thankfully, it's relatively brief. We'll examine the Inrush Code in a moment, which can be used to calculate inrush current. Power factor. The power factor entry on a motor nameplate is a measurement of how much apparent power in units of volt amperes being delivered to the motor is available for conversion into real output power in units of watts. Power factor is several things. 1, the ratio of real power over apparent power, or 2, the cosine of the phase shift between voltage and current. Motors are inductive loads and current will understandably lag voltage. Three-phase AC motors are customarily considered balanced loads, and electrical power in a balanced three-phase AC system can be calculated as follows. Apparent power S in units of volt amperes is equal to square root 3 times the line-to-line voltage times the line current. Consider the previous motor nameplate. While in the high voltage configuration and experiencing the rated load, this motor draws 3.1 amps at 460 volts. Square root 3 times 460 volts times 3.1 amps yields roughly 2.5 kilovolt amperes of apparent power. Real electrical power in units of watts is equal to apparent power times power factor. This motor nameplate indicates this motor does so at a 0.77 power factor. Roughly 2.5 kilovolt amperes times a power factor of 0.77 demonstrates this motor consumes roughly 1.9 kilowatts of real electrical power input. While we've got this example in front of us, let's discuss efficiency. The efficiency entry on a motor nameplate specifies that portion of real electrical power input that is successfully converted into usable mechanical power output. Losses might include heat, friction, noise, among others. This motor nameplate indicates this 2 horsepower motor operates at 82.5% efficiency. 82.5% of roughly 1.9 kilowatts demonstrates the motor yields 1,569 watts, or roughly 1.5 kilowatts of usable mechanical power output. A unit conversion demonstrates roughly 1.5 kilowatts is equivalent to roughly 2.1 horsepower, extremely close to the nominal or nameplate value of 2 horsepower as one might expect. It's a 2 horsepower motor. As with current, power factor and efficiency entries on a motor nameplate are specified at full load conditions and will vary considerably over the operational range. Overload conditions might be associated with more current, higher power factor, and poorer efficiency. Underload conditions might be associated with less current, lower power factor, and poorer efficiency. Oftentimes, the rated condition is a region of peak efficiency, or nearly so. We'll examine electrical properties of three-phase AC squirrel cage induction motors in greater detail in later lectures. Inrush code, or kilovolt amperes per horsepower code, or just plain code. In the event the motor nameplate doesn't explicitly specify LRA, or lock rotor amperes, this is a letter code which can be used to estimate inrush current experienced upon closure of a full voltage or direct online starter. As I mentioned previously, the initial inrush surge can be several times full load conditions and must be accounted for. Luckily, inrush conditions don't last for long, and once the rotor comes up to a rated speed, current levels out. Each letter in the Inrush code refers to a range of constants in a kilovolt amperes per horsepower chart. You can estimate inrush current by using the constant in this calculation, where inrush for a three-phase AC motor is equal to the value of the code times the mechanical power in units of horsepower divided by the rated voltage times 577. If this is a single-phase AC motor, the 577 is replaced by the constant 1000. Notice there's no I, O, or Q code, and it stops at V. It's a trick question if the motor nameplate code features letters that don't appear on this chart. As a rough estimate, most motors experience an inrush of roughly 6 times the rated current. Motors with a kilovolt ampere per horsepower code closer to A experience less, whereas motors with a kilovolt ampere per horsepower code closer to V experience more. We'll revisit inrush calculations and the electrical theory explaining inrush in later lectures, but let's try a simple example. Consider the previous 2 horsepower motor rated for 460 volts in a high voltage configuration with code K. In the high voltage configuration, we know it draws 3.1 amps. If we just wanted a quick estimate about inrush, we could say it's going to draw roughly 6 times 3.1 amps, or roughly 18.6 amps. This is an okay estimate. However, the inrush code can give us a much more accurate result. Code K represents a constant of 8 to 8.99. So let's aim for center of mass and say it's 8.495. Substituting this value, the mechanical power and horsepower, and the rated voltage into the equation demonstrates we would expect to see an inrush of 21.3 amps in the high voltage configuration. Again, luckily inrush doesn't last for long, but you've definitely got to take a 21.3 amp surge into account. Connection diagrams. The last electrical property, connection diagrams, are pictorial representations of the wiring configurations for different voltages if the motor is dual voltage, or different speed characteristics in the case of multi-speed consequent pole or multi-speed separate winding motors. This entry in the motor nameplate necessitates another independent lecture since it's pretty important. If you're following the Motors and Generators playlist in its intended sequence, it's most likely the next lecture, and I need you to remain poised in a cat-like state of alertness until then. Long story short, you get 0 points for creativity. Follow the connection diagrams exactly as illustrated, otherwise serious repercussions may result. As we learned in the electromagnetic interaction lecture available at the Big Bad Tech channel, polarity of the magnetic field is dependent upon current direction, and a motor might be damaged, or at the very least not work well if it isn't properly wired. Additionally, as we learned in the rotating magnetic field lecture, also available at the Big Bad Tech channel, swapping any 2 phases in a 3-phase AC system results in reversal of the rotating magnetic field. Hook up a motor exactly as intended and it will work as intended. Do anything else and it won't. Again, the upcoming motor connection diagram lecture deals exclusively with this aspect of the motor nameplate. The next larger group on a motor nameplate pertains to the mechanical aspects of the motor in question. The most important of these entries specify mechanical power, rated speed, design, frame, enclosure, installation class, temperature data, and duty cycle. Mechanical power. The power entry in a motor nameplate is the output mechanical power in units of horsepowers or watt, where 1 horsepower is 746 watts. As we learned in the mechanical power lecture, available at the Big Bad Tech channel, rotating mechanical power is the product of twisting force called torque in units of Newton meter times rotational speed N in units of RPM divided by the constant 9.55. Motors can be sized in one of 2 general classes, fractional and integral. Fractional motors are those motors less than 1 horsepower, like a 1/4 horsepower, a 1/3 horsepower, or a 1/2 horsepower, i.e. fractions of a horsepower. Integral motors, in contrast, are motors greater than 1 horsepower, like 1 horsepower, 2 horsepower, 5 horsepower, etc. A related property, rated speed, is the rotational speed of the shaft in units of RPM at full load conditions. Ordinarily, rated torque is not directly specified on a motor nameplate, but can be back-calculated using our understanding of mechanical power, torque, and rotational speed. An algebraic manipulation of the mechanical power formula, solving for unknown torque, demonstrates that torque is equal to the mechanical power times 9.55 divided by rotational speed. Consider the previous 2 horsepower motor with a rated speed of 1725 RPM. A unit conversion demonstrates 2 horsepower is equal to 1,492 watts, or roughly 1.5 kilowatts. Substituting mechanical power in units of watts and rotational speed into our algebraic manipulation demonstrates this motor produces 8.3 newton meters of torque at the rated condition. Related to mechanical power and rotational speed, the design or design code entry on the motor nameplate specifies the shape of the motor speed torque curve. Design B is the most common, but sometimes you'll see design D motors designed to lift loads with large static inertia. A design B motor could move a load from a dead stop at only slightly higher than its rated torque. However, design D can move a static load at almost 3 times its rated torque. As the shape of these curves imply, design D motors are designed for low-speed, high-torque applications like a crane or a hoist. We'll examine differences between design B and design D motors in greater detail in later lectures. The frame entry on a motor nameplate specifies dimensions of the motor as well as locations and dimensions of the attachment points used to mount and properly secure the motor. There are NEMA and IEC frame charts available for cross-referencing these dimensions. For example, let's say we need to know the shaft diameter of this particular motor. The motor nameplate specifies as a NEMA 56C frame. The diagram accompanying the NEMA motor chart identifies the shaft diameter as property U. It looks like a frame 56 motor has a shaft diameter of 5/8 of an inch. Enclosure. The enclosure entry in a motor nameplate identifies the level of protection taken to shield not only the motor from the outside environment, but also the outside environment, i.e. operators, for the motor's live electrical connections and rotating parts. Open motors are enclosure types that allow the passage of air through the motor to cool the windings. There are several different types of open motors, where each designation specifies the level of protection afforded against the ingress of certain size particles and from certain angles. Enclosed motors, in contrast, are enclosure types that prevent air from entering a motor. Oftentimes, these types of motors necessitate accessory components or systems to aid in cooling. Insulation class. The class or insulation class entry on the motor nameplate refers to the lifespan of the insulating material given standard operating temperatures. All else being equal, the higher the insulation class letter, the longer it's going to last at higher temperatures. A motor with Class A insulation will last 20,000 hours at 105 degrees Fahrenheit, whereas a motor designed with higher quality Class H insulation is designed to last the same 20,000 hours at 180 degrees Fahrenheit. One can estimate insulation lifespan at other than the standard temperatures using a chart like this. Let's say you got a motor with Class B insulation, and you're operating it not at the standard 130 degrees Fahrenheit, but rather an increased 150 degrees Fahrenheit. If we find the intersection of the sloped B curve with the 150 degree Fahrenheit vertical line and follow it horizontally to the left, we find this motor insulation will last only 9,000 hours. As one might expect, higher operating temperatures shorten the lifespan of a motor's winding insulation. We'll examine a special purpose tool called an insulation tester in later lectures that can quantify a motor insulation integrity. A related entry, inverter or vector duty, if it appears, would designate a motor as being suitable for operation with a motor drive. A motor drive, sometimes called a variable frequency drive or VFD or an inverter, is a power electronics device we'll examine in later lectures that can vary the excitation frequency and voltage magnitude to a motor under its direction, and thus change rotational speed and torque. Motors designed to work with motor drives have upgraded insulation and can remain cool even at reduced operational speeds. The ambient temperature entry on a motor nameplate is the maximum allowable temperature of the air surrounding the motor, whereas the temperature rise entry would be the difference between the winding temperature of a running motor and the temperature of the environment. Motors designed to be exposed to direct sun or operated in hot environments include special design considerations. Lastly, the duty cycle entry on a motor nameplate refers to the length of time a motor can be expected to run without being turned off and given a chance to cool. If the motor is designed to operate for unlimited periods without rest, it would be specified as having a continuous duty cycle, whereas if it was designed to run only occasionally, followed by a break, it would be specified as having an intermittent duty cycle. Motors intended for intermittent duty will specify the length of time a motor is allowed to run, typically 5, 15, or 30 minutes of every hour. Alright, that about concludes our brief tour of the most important manufacturer, electrical, and mechanical entries on a motor nameplate. As I mentioned previously, not all motor nameplates include all data, nor are they formatted identically. Additionally, motor nameplates may include accessory information, like service factor, which is kind of like a multiplier to a motor's permissible power rating, meaning it can be operated at a degree above the rated value without suffering damage. Electrical characteristics at service factor and/or mechanical information like bearings or lubrication might also be printed on a motor nameplate. Despite the variance in forms and entries, you should be able to interpret important manufacturer, electrical, and mechanical entries at the rated conditions for most purposes. We'll examine electrical and mechanical properties at other than the rated conditions in later lectures. In conclusion, this lecture discussed the pertinent manufacturer, electrical, and mechanical information found on a motor nameplate. This information is extremely helpful in finding an equivalent replacement motor during maintenance and repair procedures. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.